So as of this um, the time that I'm making this recording, apparently I just finished the second term for my first year in engineering. So I'd like to start on a series that would basically recount on what I've reviewed for um, differential calculus. So we'll be going through limits and then derivatives, applications of derivatives, some being word problems uh, on related rates, rate of change, optimization, critical points, mean maximum, uh, L'Hopital's rule, another way of finding the limit of a function, as well as partial derivatives, um, as well as a chain rule involving partial derivatives. So all of that will be in this series. So first, I'd like to start, of course, with the first lesson. So um, this isn't exactly calculus, but it's a prerequisite. So you just have to know these basic terms. So let's start. Okay, so we'll start at the very start. So calculus is the study of continuous change. And there are two main branches. So we have differential and integral. So the upcoming series will be about differential. I'm gonna take integral next term. So that's in a few weeks. But essentially, I'm not gonna learn about it yet. So in differential calculus, so what's involved here are instantaneous rates of change of quantities. I'm not gonna write that down anymore. As well as slopes of curves. So let's have a recall first. So what is a function? So let's say y is equal to f of x. So this is any expression that is made up of a variable as well as some constants. So let's say x squared plus 1. So constant, that's 1. Variable x, and there's a degree, that's squared. So what are the ways that we can represent a function? So we can express it verbally, numerically, visually, as well as algebraically. So what's going to be most relevant here? Um, well, this is also valid since visual, that means graphs. So you graph functions. Numerical, these are tabulated values. Verbal, of course, express it in words. But essentially, um, we'll be solving in algebra. So one example in expressing functions is in algebraic form is through explicit formula. So that's just something that you'd like to hear. You don't really have to focus on that. When you study calculus, you study how to solve, not this is just an introduction. So interval notations, we have bracket, we have parentheses, as well as set union. So this means, by the way, again, this means and or unite. So we'll see its use later. I'll show you. For bracket, this means closed interval again. And for parentheses, this means open interval. In the context of inequalities, when we say closed, the period is a shade. So let's say like that. In a number line, let's say this is 0. So this means, let's try, let's say this is a B. So since this is a closed period, so that's going to be b, and then since this is going to the right infinitely, so this is going to be positive infinity. So that kind of sort. That's how you know that we have a closed interval, if there's a shaded circle. If it were an open circle, let's say it's still b, then this is what it's going to look like. Okay. So where do we see how set union is applied? So let's say there is an open circle in the middle, and there's letter B. On top, below the circle itself. So this is gonna be expressed as negative infinity B, and then union B, positive infinity. Let's say this were a closed circle, so closed interval, we use a bracket. Okay. So let's talk about domain and range. What's the difference? So a domain means it is the set of all first elements of ordered pairs. So what we mean by first elements is that, well, we're referring to x values. For range, so it's essentially the same thing, but this time second elements, and we are referring to y values. Okay. So example, let's try y is equal to x equal to 5. X plus 5. The domain, so from left to right. So since, how do we know, how do you know if it's left to right? So what I mean by x values, in the Cartesian plane, right, this is the x-axis. So essentially, when we say x values, that's from left to right. If we're referring to y values, so this is the y-axis. So from top to bottom. Okay, so regarding the domain, since this is a polynomial function, that means basically there is no denominator. It's not a rational function wherein a fraction is involved. So that means for the domain, x is an element of all real numbers. That means, in other words, negative infinity, positive infinity. So all real numbers, like I said. How about the range? So from bottom to top. So still the same thing. X is an element of all real numbers. Same thing. Let's try another example. 1 over x plus, x minus 1. So what is the domain? So essentially, all real numbers except 1. Why? Because if you substitute x as 1, so 1 minus 1, in the denominator it's going to be 0. And that will cause the function to be undefined. So basically, the domain has to, the elements in the domain has to make sure that the function is not going to be undefined. So x equal to 1 doesn't fulfill that requirement. So it is excluded from the domain's set. Okay, so how about the range? I can't really explain why, but it's basically gonna be this. So it has something to do with 0. A rational function, by the way, is supposed to, well, by default, it's supposed to look like this in the Cartesian plane, if I remember correctly. What about a square root function, such as square root of x minus 7? So this is undefined. So the square root of 0 is undefined. So for the domain, if we make x as 7, that's going to make the function undefined. Therefore, that is not supposed to be part of the domain. That's why we exclude it. How about the range? So usually, graphically, square root functions, I'm not sure if that's the formal term, but as long as there's a square root, you call that a square root function. Graphically, it's supposed to look like this. So it's not symmetrical, as you can see. And in this case, the range is going to be 0, positive infinity. So like I said, let's say y is equal to square root of x. It's supposed to look like this. And we start at 0, basically. So that explains why we have 0 over there. If we make this square root function more complex, it is possible that the graph would look like this, or I'm not sure though, actually. But you don't have to overcomplicate it. It is better, also slightly, to know all behaviors regarding the graphs of certain functions, but essentially you just have to know this. So this is at y is equal to 0. Basically the point of origin, 0, 0. Okay, so how do you know? By the way, there's something called relation. So basically, what you have to know here is that all relations can be functions, but not all functions are... Sorry, wait. Let me rewrite what I just said. So, not all relations can be functions, but all functions are relations. Okay? So, how do you determine if a relation is a function? So, there's something called the vertical line test. So, let's say you have this graph. So, basically, to determine if a relation is a function, it should only place a vertical line anywhere. So this could be a good spot. And if the graph only intersects once with a vertical line, then that's a function. Another example. Let's say the graph looks like this. So obviously, it intersects not just in one point, 3 rather. So that is not a function. So let's move on to odd and even functions. So for odd, basically, it is symmetrical with respect to the origin. So what is that supposed to mean? Why do you have to know about the whether it's symmetrical with respect to what? So why the origin specifically? So what you have to know basically is that f such that x is negative, so f of negative x, it's equal to negative f of x. For even functions, it is symmetrical with respect to the y-axis. So you just have to know it in that order. So y of negative x is equal to positive f of x. That's the difference. Okay? It'd be great if you take that down. So what's an example? Let's say we have a function x raised to 4 plus 3x squared minus 4. So what is the... Sorry, I was about to write derivative. My bad. Force of habit. Negative x and then raised to 4 and then 3 times. negative x squared minus 4. So it's going to be equal to x raised to 4 plus 3x squared minus 4. Sorry. This is supposed to be an example for even function. Anyways, so as you can see, f of negative x is equal to f of x. These are the same. That's my point. What's an example for odd function? This. So let's say f of x is equal to x raised to 5 minus, plus 2x cubed minus 5x. How do you know if if a function is odd or even? So you see it, I believe, by the degree of the polynomial. So yeah, the degree is odd or even. That dictates whether the function is even or odd. So it's going to be this, and then this, and then this. So it's basically the exact opposite in terms of the signs. So yeah, that's it. By the way, the graph of this function, so it looks basically like this. The lowest point is, I'll be honest with you, I don't remember anymore. But that's basically what it looks like. This point, you'd know it from somewhere here in the function itself. It's probably the constant, but I can't verify. I don't really remember it, like I said. Let's say here, so in the even function example, it looks like this in the graph. So symmetrical with respect to the origin. That's what it looks like. It is symmetrical. Okay, you might want to know this as well. So what about this other example? So it's still the same thing as a while ago. Sorry, not that, this. But we add a constant. Is it still odd? No. Well, it's for the same reason. It's because of the constant. So f of x is not equal to f of negative x. Okay, let's go to... This is just going to be fast. Increasing and decreasing functions. So say this is a, this is b, c, and d. So for a, b, from a to b, it's a decreasing function. So your y decreases and then your x increases. Let's say b to c, that's going to be an increasing function. So your y increases and your x increases also. Okay, composite functions. Let's have a short recall. So let's say f of x is 3 over x and g of x is equal to x squared minus 1. So let's find f of g of x. Now, what does that mean? So as you can see, the one that's outside is this. So we write that down, and the x, you substitute that with whatever is inside. So that's g of x. G of x is x squared minus 1. Basically, substitute this at the x value of f of x. So it's going to look like this. That's it. How about the other way around? G of f of x. So the x here will become this 3 over x. So It's gonna look like that. 9 over x squared minus 1. Okay, that's it. Limits of a function. Okay, we're done with the recall. We're actually gonna start calculus now. So the value of a function approaches as input variable approaches a certain point. So what do I mean? Basically it's this. So I'll repeat it. The value of a function approaches as input variable approaches a certain point. So yeah. By the way, you want to know that limits, this is basically the backbone of calculus. So let's have a rundown on the theorem of limits, the theorems. So the limit of c as x approaches a is still c, assuming that x is a constant. Okay? And then limit of f of x, limit c f of x as x approaches a, you can rewrite it basically as this. So something similar, I'd tell this to you now. Something similar is shown here in the context of derivatives. So usually if you want to derive, let's say, I want to give an easy example. I will spoil you something on partial derivatives. Let's say xyz. But you're going to assume that y and z are constants. X is, well, you want to find the derivative of x. So in that case, you put the constants at the left side, and then what you want to derive will be here. In that case, that would be x. Derivative of x is just 1. So the answer is going to be yz. Anyways, partial derivatives is a long way ahead. So yeah, applying that knowledge here, you separate the constant and you focus on the function itself, f of x, finding its limit. So yeah, number 3. So we want to presume that the limit of f of x as x approaches a is equal to L, and the limit of g of x as x approaches a is equal to r. So what does L and R mean? Basically left and right. So plus minus basically distribute the limit. So it's gonna be in other words that. What about multiplication? So let's say so it's basically just gonna be multiplication. Okay. What about division? So again, same concept. You just distribute the limit sign. How about this? There is an exponent from the outside. Well, you just you just write it as is. You could also express it as this basically, or just L raised to n. What about for square root? So it's gonna be like this. Okay. So generally, you solve for the limit of f of x as x approaches a. So, well, usually the most basic way to solve for limits, it's supposed to be the by direct substitution. Um, so, for example, actually I'll show an example later. Let me just tell you now, direct substitution doesn't work all the time. There are 3 exceptions um, that makes direct substitution not the right way to solve. So one of them is when the denominator of a function will be equal to 0 if you substitute. So for example, so 1 raised to 3 minus 1 over 1 minus 1, that's obviously going to be 0 over 0. This is undefined. And anything that's divided by 0 is undefined. So we want to avoid that by applying any of the following. So we could factor, we could rationalize, or we could use trigonometric identities. Okay, so let me give some examples when solving for limits using manipulation, algebraic manipulation, or basically factoring. So same example as a while ago. What do we do? So I hope you know your identities. I'm not sure if that's the right way to call it, but here we could rewrite this as this, and we could rewrite that as that. So that's for the numerator. What about the denominator? Just copy. Now we can find something that we could cancel. So from there, we no longer have a denominator, so we can start to direct substitute. So that's gonna be 1 squared plus 1 plus 1. That's equal to 3. So that's the answer. Let me spoil something. Another way of solving this, let's say, by L'Hopital's rule. Although I'm gonna formally teach that in another video. Let me show you. Okay, so one principle in L'Hopital's rule is that you want to express the function first as f of x over g of x. You know that a certain problem could be solved using L'Hopital's when you try to direct substitute, the denominator is going to be 0. So essentially we have 4 cases of indeterminate forms, the most basic of which is 0 over 0, or another is infinity over infinity, but you don't have to know that yet. So essentially here, as we've seen earlier, if we direct substitute, it leads us to 0 over 0, so that's indeterminate. So, and our fraction is already, well, it's already in this form, so we don't have to change anything. We just have to start deriving. So derive the numerator and denominator separately. So that's basically it. And then start substituting. So x is equal to 1. 3 times 1 raised to 2, that's going to be equal to 3. That's it. As easy as that. Derivatives, by the way, if you don't get it yet, I'll teach that in another video. It's coming soon, real soon. Another example, but this time when well, it shows where we apply rationalization. So multiply both sides by, hang on, yeah, that's what we do. Multiply both sides by 5, and then you just copy the entire thing, just the opposite sign. So here it says minus, so we put a plus. Let's see first, by the way, before rationalizing. It's obvious that if we substitute x as 7, it's going to equal to 0. So the denominator is 0, so we do need to find a different way. So here, 25, FOIL method. So we end up with that, and then below, okay, simplify the numerator. We'll get this. So factor 3. We're gonna have this. Cancel. And then start substituting. X is 7, right? So 3 times 7, that's 21, plus 4, 25. Square root of 25. Well, in this case, by the way, one careless mistake. You multiply both sides with a plus, right? Why did I write minus? Avoid that mistake. So we're gonna have basically 3 over 10. That is the answer. How about solving using trigonometric identities? Let's say limit as x approaches pi over 4. So we have cosine 2x over cos x minus sine x. By the way, if you know your trig, pi over 4 is equal to, in the unit circle, 643. This is 45 degrees. What I mean by 643 is this one is pi over 6, pi over 4, pi over 3. This is in quadrant 1 of the unit circle. 3, 5, 7. I don't really remember the other quadrants anymore. But essentially, it's still pi over something. So if we direct substitute cosine 2 times 45, that's going to be 90. And then cosine 45 minus sine 45. In the unit circle, pi over 4, it's basically square root of 2 over 2 and square root of 2 over 2 cosine sine. So this is basically going to equal to 0. Cosine 90 is, let me recall, cosine 0 is 1. Cosine 90, well, it's going to equal to 0. Cosine 180 is equal to negative 1. Cosine 360 is equal to 1. Sine 0 is equal to 0. Sine 90 is equal to 1. Sine 180 and 360 are all equal to 0. That's all from memory. It helps a lot. You're supposed to know that already by the time you reach calculus in college. So cosine 90 is 0, right? So still 0 over 0. We need to do something. Good thing, since this is cosine 2x, there's an identity for that. So that is going to be equal to, well, for one of its forms, if I remember correctly, it's like that, or I can't really confirm though, but for sure, this is another form. I can verify this is correct. So let's use that. So cosine 2x in the numerator is going to be written as that. And below, we have cosine x minus sine x. In the numerator, we could rewrite it as this. Cancel. So we have this instead. Let's start substituting already. So cos 45 plus sine 45, well, that's gonna be square root of 2 over 2 plus square root of 2 over 2. This is the answer. Cancel. Okay. So that is it. I'll make a part 2. I'm tired. Thanks for watching.